Okay, last video for chapter 3, we are looking at empirical and molecular formulas. So just a kind of a recap from intro chem, example I always use, I don't know why, but benzene is C6H6, right? That is the true formula for benzene. And it's called the molecular formula, right? Covalent compound, so it's a molecular formula, the true molecular formula. The empirical formula is how we could simplify this to the simplest whole number ratio. So instead of C6H6, it could be CH. That would be the empirical formula. Now the empirical formula is not the true formula. All it tells you is that in benzene, for every one carbon, there's one hydrogen. That's it. That's all it tells you. Empirical formulas are really helpful in organic chem when most of your compounds are just carbon, hydrogen, maybe some oxygen, nitrogen, or sulfur. And they can give us a lot of information, but they're not typically used with ionic compounds as much. So what we're going to do is we're going to first learn how to determine an empirical formula and then figure out how to get the actual true formula from that. So the first thing is, when you are determining an empirical formula, the first thing you need to know is the mass of each element that's in that compound. And there's two ways that you can do this. The first thing is, if you're doing an experiment in lab, you could take an element and then add it to another element. For example, last semester we took magnesium and combined it with oxygen from the air. And you can track the mass of element that you start with and the mass that you picked up from the air. And you can get your mass of each element in the compound that way, your mass of magnesium, your mass of oxygen. The other way we can do this, though, is through a machine called a GCMS. So you have a compound, you don't know what it is, you give it to the machine, and the machine can give you that percent composition. It can say, hey, this compound is 21.26% carbon and 4.86% hydrogen, etc. If you have a mass percent, then just take that mass percent and assume that you have 100 grams of compound. So if I have 22.86% carbon, that means I have 22.86 grams of carbon. So your percent sign just becomes your grams, which is easy. Then what you want to do is, like with everything in chemistry, you convert mass to moles. And we do that using the molar mass values from the periodic table. The problem at this point, though, is that even though that will help us with the formula, right? If we have a C6H6, that 6 to 6 ratio is moles. For every 6 moles of carbon, there's 6 moles of hydrogen. After we get the number of moles of each element, they're not going to be pretty numbers. So we simplify by dividing all number of moles by the smallest. And a lot of times at that point, we will have a nice whole number ratio, like 1 to 1 or 1 to 2. But if we don't, we may need to use a multiplier. And there are some scenarios there. If you after you're dividing by the smallest, you get something that ends in a fifth, like a fraction of 1/5, 2/5, 3/5, 4/5, right? 0.2, 0.4, 0.6. Then your multiplier would be a 5. If you get a 0.25 or a 0.75, right? That's either 1/4 or 3/4. So your multiplier would be a 4. A 0.33 or a 0.67, that's either a third or 2/3. So your multiplier would be a 3. And a 0.5, right? That's a half. So your multiplier would be a 2. So let's work an example, all right? So this one is going to be that mass example, like I said, for working in lab. We've got 24.5 grams of nitrogen reacted with 70 grams of oxygen to form a binary oxide compound. What would the empirical formula be? So we've got 24.5 grams of nitrogen and 70.0 grams of oxygen. Now, if anybody is thinking about the diatomics, right, nitrogen's really N2, oxygen's really O2, you don't want to use that here. So Hofbrinkel doesn't come into play here with empirical formula, because when the compound is formed, if the nitrogen was present in the air as N2, that nitrogen bond first has to be broken. So you're always adding just a singular nitrogen and a singular oxygen to form whatever compound you're going to form. So we got 24.5 grams of nitrogen. We're going to divide that by the 1401 molar mass. And we're going to keep our sig figs. So keeping 3 sig figs, we have 1.75 moles of nitrogen. We have 70 grams of oxygen. We're going to divide that by the molar mass of 16. And that means we have 4.38 moles of oxygen. All right, at this point, we want to simplify. We divide by the smallest. In this case, the 1.75 for the nitrogen is the smaller. So when I take 4.38 for oxygen, divide by 1.75, I get 2.5. All right, so what I found here is based on my mass of nitrogen and mass of oxygen, is that for every 1 nitrogen, I have 2.5 oxygens. And because I've got a decimal of a 0.5, right? We said that that's like a half. We're going to use a multiplier of a 2. And when you use a multiplier, you use it to all elements. So instead of 1 nitrogen, we have 2. Instead of 2.5 oxygens, we have 5. So N2O5, if we were going to name that, we would say it was dinitrogen, and then penta or pentoxide. All right. So if instead you have a percent composition, like in the next example, like I mentioned, we're just going to assume that we have 100 grams. So if our compound is 71.95% carbon, that means 71.95 grams of that 100 grams would be carbon. 12.08% hydrogen would be 12.08 grams hydrogen. And 15.97 grams would be oxygen. So we have the mass of each element. First job, always go to moles. So we're going to divide by the molar mass of each of these. Molar mass, again, right from the periodic table. So for the carbon, 71.95 divided by 12.01, I have 5.991 moles of carbon. For the hydrogen, 12.08 divided by 1.01. I have 11.96 moles of hydrogen. And then for the oxygen, I have 15.97 divided by 16, and I get 0.9981 moles of oxygen. So at this point, to simplify, divide through by the smallest, which is the number of moles of oxygen. So oxygen will simplify and go to 1. And then let's do the other ones. So carbon, we're going to take 5.991 divided by 0.9981, and we get 6. 11.96 for the hydrogen divided by 0.9981, we get 12. Right? So we don't need a multiplier for this example. We got nice whole numbers. So that is our empirical formula, C6H12O1, and you don't have to write the subscript of 1, you just write it as O. All right, so that would be hexanol or cyclohexanol. All right, and again, that is an empirical formula. That may not be the true actual formula, but what we know about this compound is for every 6 carbons, there's 12 hydrogens and 1 oxygen. Now, how do we follow that up and then try to figure out what the true formula is? So what I always thought about was that the empirical formula was like a repeating unit. So the example I gave earlier, the benzene, right, the C6H6, that empirical unit of CH repeats 6 times. So what we want to think about is the empirical formula, if in this case the CH, the mass of that would repeat 6 times until we get the mass of C6H6. And the reason why we focus on the mass of it, which is really the molar mass, is because those same machines that can give us percent composition data, they can also give us the molar mass of the compound. So that's why that's helpful. So I've got an example here. It says we've got ethylene, which has a molar mass of 28 grams, cyclohexane, which has a molar mass of 84 grams, and 1-pentene has a molar mass of 70 grams. They all have the empirical formula of CH2. So each of those 3 compounds has 1 carbon for every 2 hydrogens. But what would be the true formula for each of those? So what we're going to do is we're going to take that empirical formula of CH2 and find the molar mass. So 12.01 for carbon, 1.01 for hydrogen, but taken twice. So we get 14.03 grams per mole for the molar mass of that empirical formula. Then what we're going to do is we're going to take the molar mass of the true compound, divide it by the molar mass of the empirical, and that will tell you how many times that empirical formula repeats to make up the true compound. So the repeating factor is what I call it. So what I'll do here is for the ethylene, you have a molar mass of 28 grams, and our empirical was 14. So that means a repeating factor of 2. So instead of 1 carbon and 2 hydrogens, it must be 2 carbons and 4 hydrogens. So ethylene must be C2H4. The next one is the cyclohexane, which has a molar mass of 84 grams. And if I divide that by 14, I get 6. So that means instead of CH2, it's C6H12. All right, and hex means 6 carbons, ETH means 2 carbons. When you get to organic, you'll see that. And then the last one here is the 1-pentene. And that one had a molar mass of 70 grams. Divided by 14 is a repeating factor of 5. So instead of CH2, it's C5H10. And penta, right, means 5. So that's why there's 5 carbons there. So in each of those examples, you take the molar mass of the true compound, divide it by the molar mass of the empirical, and that'll tell you how many times it repeats. Now, in this case, you don't use multipliers. That repeating factor has to be a whole number. All right, so let's do one final example, kind of pulling all of this together. It says we have adipic acid, it's 49.3% carbon, 6.9% hydrogen, and 43.8% oxygen, and the molar mass is 146 grams per mole. Let's do the empirical and molecular formula here. All right, so I'm going to go ahead and do the empirical formula first. So I have 49.3 grams of carbon, 6.9 grams of hydrogen, and 43.8 grams of oxygen. We're going to divide by the molar mass of each of those elements to go to moles. So for carbon, 49.3 divided by 12.01, I get 4.10 moles of carbon. And keep all your sig figs, keep track of those, because if you round too early, it's going to really make it messy. So 6.8 moles of hydrogen. And then for the oxygen, I have 2.74. All right, now we divide by the smallest. So the number of moles of oxygen is our smallest. So we're going to divide all of those previous numbers by 2.74. So for the carbon, 4.1 divided by 2.74, I get 1.50. The 6.8 for the hydrogen divided by 2.74, I get 2.5. All right, so I have two elements that end in a 0.5. That means a multiplier of 2 to get to whole numbers. Remember, if you do the multiplier, do it for all elements. So we would have C3H5O2. That's the empirical formula for adipic acid. All right, now last step to get the molecular formula. We're going to take the molar mass of the true compound, which was given to me in the question. It says that the true adipic acid weighs 146 grams per mole. And then I want to divide it by the molar mass of my empirical. So 3 carbons at 12.01 apiece, 5 hydrogens at 1.01 apiece, and 2 oxygens at 16 apiece. So I'd have 36.03, 5.05, and 32. And if I add that together, I get 73.08 for my molar mass of that empirical unit. So 146 divided by 73 is 2. So that means multiplying everything through by 2. So C6H10O4. So that would be my true molecular formula for adipic acid, with an empirical formula of C3H5O2. All right, so that completes chapter 3.